Capacity. Specific heat capacity is the term we have for how we determine how easy it is to heat or cool a substance, how easy it is to change the temperature of a substance. Some substances are easy to change the temp of. They have a low specific heat capacity, and some substances are hard to change the temp of. They have a high specific heat capacity. Metals have a very low specific heat capacity. They are easy to change the temperature of. Think about it. If I hold a lighter to a piece of metal for a few seconds, you are not going to want to take it from me, right? Because it's going to have heated up very quickly. It'll also cool down very quickly. If you take that hot metal, wave it around, okay, it'll cool down very quickly as well. Um, Water has a very high specific heat capacity. If I take a lighter and I'll hold a lighter to this water for a couple seconds, I would put my hand in here, right? It's not going to be scalding hot, okay? Because water is very hard to change the temperature of. You got to put a lot of thermal energy in to change the temperature of water. It has a high specific heat capacity. So this is what specific heat capacity tells you. Specific heat capacity tells you how easy or hard it is to raise the temperature of 1 gram of a substance 1 degree Celsius. Metals tend to have low specific heat capacities, and other substances tend to have higher specific heat capacities. We abbreviate specific heat capacity with a letter C that stands for specific heat capacity, and it usually has really weird units of like joules per gram times degrees Celsius. It can also be, instead of using joules per energy, it could be in calories per gram times degrees Celsius. So specific heat capacity has pretty crazy units because it's the amount of energy needed to raise a gram of a substance 1 degree Celsius. So it's got to have those 3 units in it to make it all kind of work out. This is an old way of writing the formula. Nowadays, we tend to use Q equals mcat for this. So this is the formula I would suggest you memorize instead of delta E equals S times M times delta T. We used to use an S for specific heat capacity. Now we use a C, whatever. If you want to change the temperature of a substance, the amount of heat that you need to put in depends on 3 things. It depends on the material, the specific heat capacity, that's the C. It depends on the mass of the sample you're trying to change the temp of, and it depends on the temperature change you're trying to accomplish. So I think if you sat down and really thought about this, most people could get here on their own, in fact. If I want to change the temperature of water, number one, I need to know how hard it is to change the temperature of water just in general, right? I need to know its specific heat capacity. It's going to be 4.184 joules per gram times degrees C for water. Okay, but then I also need to know what's the mass of the water I'm going to change, because if I'm only changing 250 milliliters of water, that's going to take way less energy than if I'm changing 2.5 liters of water, right? So 250 milliliters versus 2.5 liters, right? The more you have, the more energy it's going to take. Also, what's the temp change you're going to try and achieve? Am I just going to take this from 25 degrees Celsius to 35 degrees Celsius? Or am I going to try to take this from 25 degrees Celsius to 90? Obviously, the greater the temp change you're trying to achieve, the higher the amount of energy will be needed as well. So Q equals MCAT. The amount of heat is equal to the mass of the sample times the specific heat capacity of the sample times the change in temperature of the sample. So let's give this a shot. Let's do our first Q equals MCAT problem. So how much energy is required to heat a 19.1 gram sample of aluminum from 91 degrees Celsius to 110 if the specific heat capacity of aluminum is 0.89 joules per gram times degree C? So let's give this a shot. We're going to use Q equals MCAT. I'll put the time signs in there. And I don't have the delta symbol on hand, so we're just going to do a T for change in temp. Whoops. That's change in temp. So the amount of heat energy is going to be equal to the mass, 19.1 grams, times the specific heat capacity, 0.89 joules per gram times degrees C, times the change in temperature, we're going from 91 to 110. That's a 19 degrees Celsius temp change. And let's calculate that. Take a look. Grams are going to cancel out. Degrees Celsius are going to cancel out. And we're going to be left with an answer in joules. So 19.1 times 0.89 times 19. That's going to be 323, 2 sig figs, so 320 joules. If you want to heat up a 19.1 gram sample of aluminum from 91 to 110 degrees Celsius, you'd have to put in 320 joules of energy. All right. Try this one. This one's a little bit more difficult. What will be the final temperature of a 400-gram piece of copper that has 65.5 kilojoules? Be careful of that unit. That's in kilojoules. Specific capacity is in joules. So you're going to have to change it. Of heat added to it, the initial temperature of the copper is 18 degrees Celsius. Specific heat capacity of the copper, 0.386 joules per gram times degrees Celsius. Why don't you try to pull some stuff out of that while I copy it down on the board and pull some stuff out? And we'll talk about how to use Q equals mcT to solve this guy. Hopefully you were able to pull this stuff out. We want the final temp. The mass of the sample is 400 grams. The amount of energy Q that went in, 65.5. The starting temp was 18, and the specific heat capacity of aluminum, 0.386 joules per gram times degrees C. So I'm going to write the formula up here. Q equals mcT. And let's kind of look at what we have. We have Q, we have the mass, we have the specific heat capacity. We're looking for the change in temp. So if we divide both sides, well, we're looking for the final temp, but we're going to get the change in temp first, and then it's easy to get there from there. So we'll talk about that. So if we divide by m times c, the change in temp is equal to Q over m times c. Now we got a problem. We cannot just use 65.5 kilojoules and 0.386 joules per gram times degrees C, because kilojoules and joules aren't going to work. So I would convert the kilojoules to joules. So 1 kilojoule is 1,000 joules. And that's going to be 65,500 joules. So the change in temp is equal to 65,500 joules divided by the mass, 400 grams, times the specific heat capacity, 0.386 joules per gram times degrees C. Joules cancels out, grams cancels out. Degrees Celsius is in the denominator of a denominator, which means it goes to the numerator, and we're going to get the change in temp. The change in temp would be 424 degrees Celsius. 424 degrees Celsius. So here's the thing, okay? We want the final temp, and we just got the change in temp. Well, T final is going to be equal to, I'm sorry, let's derive it. The change in temp is going to be equal to T final minus T initial. So if we add the initial temp to both sides, the final temperature is going to be equal to the initial temperature plus the change in temperature. Think about it, folks. Okay, we're starting at, let's say, 18. We're going to change by 424. What will be the new one? Well, 18 plus 424 will be your new temp. So here we go. 18 degrees Celsius plus the 424 degrees Celsius temp change. That's a 442 degrees Celsius temp change, or final temp. So we changed by 424, but since we started at 18, we're at 4. Now, if we started at 0, the change would be the final, right? But since we started at 18, that's a 442 degrees Celsius final temp. So this formula, Q equals mcT, very handy, right? Allows us to predict what new temperatures would be, allows us to determine how much energy we got to put in, would allow you to determine the mass of a sample, all that stuff. You can solve for any one of those four things: heat, mass, specific heat capacity, or change in temperature. All right. Molar heat capacity is sometimes used, and molar heat capacity is pretty easy. Instead of giving the amount of energy needed to raise a gram of a sample 1 degree Celsius, we can do the amount of energy needed to raise a mole of a sample 1 degree Celsius. And it's very easy to go from a specific heat capacity to a molar heat capacity. You just multiply by the molar mass of the substance. Think about it. If I take joules per gram times degree C times a molar mass, the grams cancel out, and I'm left with joules per mole times degree C, which is my molar heat capacity. Cool. We did Hess's law. We did standard enthalpies of formation. We did average bond dissociation energies. What do we got left? Heat transfer problems. Oh, boy. And then we got to talk about calorimetry, which is our lab zone. So last thing, and then we'll mention what calorimetry is, but you're going to learn what calorimetry is tomorrow. So thermal heat transfer problems, these can be kind of a pain, but if you stay organized, they're not that bad, I promise you. So here's how this works. A heat transfer problem is when you take a hot object and put it in a colder object. So a lot of times if you take a hot piece of metal, put in like a cup of water, right? What's going to happen? The hot object is going to give thermal energy to the cold object. So the hot object's temperature is going to go down, and the colder object's temperature is going to go up until they eventually meet in the middle and reach a state of what's called thermal equilibrium. So the hot object is going to cool down till this single point, and the cold object is going to warm up, and eventually they will become the same temperature at what is called their thermal equilibrium. Now, the way this works is we assume that the total amount of energy, given to the system is equal to the total amount of energy lost by the other substance. So essentially, what we do is we do two Q equals MCAT problems, but we make the one side completely negative. Okay, so these can be really tricky, lots of algebra. Let's look at one of these problems, and I'll show you how it works. So let's do this guy. A 32.5 gram cube of aluminum at 45.8 degrees Celsius is submerged in 105.3 grams of water at 15.4 degrees Celsius. So let's just stop there and think. We're taking a warm cube of aluminum, 45.8 degrees Celsius, and we're putting it in a colder cup of water, 15.4. The aluminum is going to cool down. The water is going to heat up. They're going to meet somewhere in between. And I want to know what that final temperature will be when they meet. Give me a second to write this all down. You need a decent amount of paper or room here. So if you're near the bottom of a sheet of paper, I would start a new one, folks. Because these problems this is going to take up this whole board probably with algebra. Let me extract the information here. Here's how this works, folks. What we need to say is that the heat lost by the one substance, let's say aluminum, is going to be equal to the opposite heat gained by the other substance. So it doesn't matter which one you make negative. So I'm going to make the water one negative. So here's how this works out. Q equals MCAT, heat equals mass times heat capacity times change in temp. So the mass of the aluminum times the specific heat capacity of the aluminum times the change in temperature of the aluminum equals the negative quantity mass of the water times specific heat capacity of the water times change in temperature of the water. Take a second, write that down. So hopefully what you see, Q equals MCAT, Q equals MCAT, right? So the mass of the one substance times its specific heat capacity times its change in temp has got to equal the negative quantity mass of the other substance times the heat capacity times its change in temp. So now we can start filling in values. So the mass of the aluminum, 32.5 grams, times the specific heat capacity of the aluminum, 0.903 joules per gram times degrees Celsius, times the change in temperature of the aluminum. Okay, what's the change in temp? Well, that's going to be T final minus the initial temperature of the aluminum, which was 45.8. That's going to equal negative, uh-oh, I'm out of room. This is not going to be pretty. That's going to equal negative quantity mass of the water, 105.3 grams, times specific heat capacity of the water, 4.18 joules per gram times degrees C, times the change in temperature of the water, which is going to be T final, minus the initial temperature of the water, which the initial temperature of the water was 15.4. Woo! All right, now we're going to start combining stuff. It's going to get a little cleaner. I'll be able to fit it in. So grams are going to cancel out here on both sides. Let's multiply these two before we distribute. So 32.5 times 0.903, that's 29.35 joules per degree C times the quantity TF minus 45.8 degrees C. We're going to distribute here in the next step. I just multiplied those two. Now I'm going to multiply these two. Negative quantity 105.3 times 4.18. That's 440.2 joules per degree C times T final minus 15.4 degrees Celsius. Okay. Now I need to distribute the 29.35 joules per degree C in. The degree C are going to cancel out on that guy. And then I need to distribute the 404.2 in. So here we go. 29.35 joules per degree Celsius minus whatever that is. 1,344 joules. That equals, I'm going to leave that negative out still, 440.2 joules per degree Celsius minus 15.4 times 440, oops, 40.2, 6,779 joules. The degrees Celsius will cancel out. Now I'm going to distribute that negative in, so that becomes a negative 440.2 joules per degree Celsius plus, well, it's negative 440 joules per degree Celsius times TF. I missed the TF on both sides. Cool. So what do we end up with? Well, my goodness, after some algebra, we get 29.35 joules per degree C times TF minus 29.35 times negative 458. That's 1,344 joules. The degree Celsius canceled out there. Then we get 440.2 degrees Celsius times TF minus 6,799 joules, but then I distributed the negative, so negative 440.2 joules per degree C times TF plus 6,779 joules. Now I need to combine like terms. Okay, think of the TF like an X, right? So we need to get those all over and those all over. So I'm going to do two things here in one step. You ready? I'm going to add 1,344 joules to both sides. And I'm going to add 440.2 joules per degree C times TF to both sides. That's going to cancel out. That's going to cancel out. We're going to get the sum of those two. So 440.2 plus 29.35, that's 469.55 joules per degree C times TF equals whatever that is. 8,123 joules. We're going to divide by 469.55 joules per degree C. Joules cancels out. Degrees Celsius is in the denominator of the denominator. Here we go. 8,123 divided by 469.55. And we get 17.3 degrees Celsius. Woo! What does that mean? Here's what that means, folks. Okay, you got this cup of water here chilling at 15.4 degrees Celsius. You drop this hot piece of metal at 45.8 degrees Celsius in there, and the whole system, the metal cools down, the water warms up, they meet in the middle between 45.8 and 15.4. They meet in the middle at 17.3 degrees Celsius. That's where they would reach thermal equilibrium when the metal's done cooling and the water's done warming up. 17.3 degrees Celsius. Those problems there's a decent amount, right? Okay, that's tough. That's tough. Algebraically, you got to stay super duper organized, right? Okay, and we can work another one of those on Wednesday if you want before the test. I'll be happy to do that too. Last thing I want to mention is what calorimetry is, and that's what we're doing in our lab tomorrow. We are going to be doing constant pressure calorimetry, also known as coffee cup calorimetry. Constant pressure calorimetry or coffee cup calorimetry. That's just when you use a well-insulated container to keep all the energy from a chemical reaction inside. So if it's an exothermic reaction, if I mix the stuff together, which is what you're going to do tomorrow, when you mix the stuff together, if it releases heat, we want all that heat to stay in here. Okay, and if it's endothermic, we want all the heat to come from in here, right? So if it's cooling down. So what you essentially do, oftentimes with coffee cup calorimetry, the thing that's heating up or cooling down is water. So if we know the mass of the water, we know the specific heat capacity of water is 4.18 joules per gram times degree C. And if we can get the change in temperature of the water, we can get the heat. Okay, so it's actually a pretty, unfortunately, boring kind of experiment. You measure the initial temperature. Okay, when you start the reaction. It usually, like if it's exothermic, it heats up. You measure the highest temperature reached, and you can get the change in temperature. A calorimeter is nothing more than a well-insulated container that allows you to get the change in temperature for a reaction when you're studying the thermodynamics. That's all it is. And we'll talk about it in way more detail tomorrow.